Good morning, everyone, and welcome to the second ilifu training session that we're hosting. This is going to be covering more advanced topics. So we covered a basics training session a couple of weeks ago, and this basic training was recorded, and we're going to put it up on the video up on the ilifu website. And this session will also be recorded and will be posted on the website along with the accompanying slides. I just wanted to quickly introduce our support team. So myself, I'm Jeremy Smith and the ilifu operations manager. And then Jordan Collier is the astronomy support person, and Dane Kennedy. I guess if you guys want to wave and identify yourselves, you're welcome to. Dane Kennedy is from bioinformatics support. And then there's Mike as well, is with us today, and he does a lot of system and operations support. I just wanted to reiterate the channels for support. So our primary channel for support is emailing us at support@ilifu.8.za. This goes to a ticketing systems, and all the support staff have access to this. So it's our primary channel for support, because your ticket will be responded to in a very quick fashion, because there's a number of users behind the ticketing system. I mean, a number of support staff behind the ticketing system. The other ways that you can get help or find information is through the user documentation. So that is at docs.ilifu.ac.za. Just wanted to provide a quick demo of this website. So this is our ilifu user documentation, and it's broken up into a getting started section, which provides step-by-step process for accessing the system, issues with your SSH keys, how to use the different services, submitting jobs on SLURM. So these are more basic topics, and then advanced topics are covered under technical documentation, specifically in the astronomy and bioinformatics domains, and then more general topics covered here too. We also have the system status page now, which is a new feature that we support, and that can be found at status.ilifu.ac.za. So this will just show what the current status of the system is, and you can drill down into different services on the cluster and find out more information whether something is operational or not. And then, as mentioned, we also have the training videos that are available on the ilifu website. In terms of the topics that we're covering today in the advanced training, our original scope we found was a bit ambitious, so we've decided to have a second training that we will host in 2 to 3 weeks' time. But for today's topics, we'll be covering advanced SLURM usage, so the different commands and possibilities on the cluster using SLURM. We'll cover parallelism on the cluster and how to use software that supports parallelization. And then we use the pipelines astronomy software as a case study to implement this, and how to basically develop a workflow or pipeline on the cluster. And then we'll cover slightly more in-depth topics about data transfers, and finally we'll do a demonstration of the astronomy visualization tool called CARTA. So Jordan Collier is going to take this training session today. And then the topics for the second training session is going to be covered in 2 to 3 weeks' time. And this is going to cover singularity and how to use and build your own container, how to use containers as kernels in the Jupyter environment. We'll talk about using Python virtual environments and other virtual environments on the cluster. And then we'll also speak about R containers and using RStudio, and Nextflow, which is a tool that's used a lot by the bioinformatics users. And we'll also cover the topic of using the Surveyor archive. This has some advanced features that have been recently implemented. So we'll cover this in training, advanced training too. Just to point out that today's Session will be run for about 45 minutes, and then there'll be a period for questions at the end of the training session. You're also welcome to propose or put forward ideas for topics to be covered in these training videos. So we appreciate the feedback. I'm going to hand over to Jordan Collier now, who will take you through the Advanced Training 1 session. Thank you.
Thanks, Jeremy. Can you hear me all right?
I can hear you fine.
Great. I'm just going to share my whole desktop here so you can see the browser there and the slides there. Cool.
I can see the slides, Jordan. It's not in a presenter view at the moment.
Yeah, that's fine. Is that the browser
That's
as well?
the website. Yeah.
Great. Okay, thanks, Jeremy. So picking up where we left off last time, we're going to jump straight into talking about SLURM. So
Jordan,
to remind you, this is...
Sorry, you're a bit quiet. You might want to up your sensitivity again.
Is it? Okay. That's what the little test was before, but we can change it. It's actually at maximum already, so I don't know if you want to turn up.
Jacinta, I'm able to hear Jordan all right. Do you want to try to turn up the volume on your side?
Maybe it's, yeah, maybe your voice is okay. Jordan's a bit quiet, but it's okay.
Okay.
Okay, sorry about that. I tried to project my voice as well. Yep, so picking up from where we left off and jumping straight into SLURM. Again, you can find documentation about this on the website. But to remind you, SLURM is the tool that we use to manage the resources on the ilifu SLURM cluster. So this is something that has multiple nodes, which we consider as individual computers or machines. And so in order to access those, you need to kind of have some sort of software that manages your job submission to those nodes and is able to allocate you those resources and so on. And so to remind you of the picture, we have this login node, which is where you land when you log into the SLURM cluster. We can also call this the head node. And this is what you use for managing your jobs and their submission. And so you can run your SLURM commands here that we talked about last time, like saccount, srun, and sbatch, and so on. But you're not supposed to run your heavy processes or your software here. In fact, we don't have Singularity, which is our software for managing containerized environments, where you can run a particular process with all the software available within the container. Singularity isn't available on the login node, and so you hopefully won't be able to run that anyway. Where you do want to run your processing is on a compute node, and this is what's listed at the bottom of this figure as the SLURM worker nodes. We can also call them worker nodes, and this is where you run your heavy processing or your software via Singularity containers. Now we have quite a number of partitions with different resources and for different purposes. You can list these with sinfo. So for instance, in the main partition, we have 79 nodes. Each of those has 32 CPUs and then 236 gigabytes of usable memory. And this is what's listed as SLURM Worker 101 and so on. There's 79 of these. We also have the high mem partition. This is 2 nodes, each has 32 CPUs, but then also 482 gigabytes of usable memory. And so this is for where you want to run processes that require much memory, where you're not able to utilize memory across multiple nodes, but you're restricted to one at a time. If your software can run across multiple nodes and utilize the shared memory across those nodes, then you don't need to use the high memory partition. You could rather just use the main partition, but request many nodes at once. And I'll talk about this a little bit later and how you might do this. And then we've got the GPU partition, and this is 3 nodes, each with 2 GPUs and 236 gigs of RAM. And this is listed as SLURM Worker 401 to 403. And so we have quite a number of advanced user commands that I'll be covering. All of these you can get from the SLURM documentation. I've listed the URL there, and it shows you the long and short form of various parameters that you can pass into the SLURM command. So for instance, in this case, I have option O. This is the shorthand. And then later on, I have option partition. This is like the long form. You could also do option P for this. So I kind of interchange between them. But if you want to see the parameters in their short and long form, you can look at the documentation at this URL. So each of these you can pass into different SLURM commands. So for instance, srun and salloc both accept partition. sbatch also accepts partition. So what I'm demonstrating is the individual parameters, but it's not only specific to the SLURM commands that I'm showing. Hope that makes sense. So before running your jobs, you might want to look at the available partitions and their specifications. So you could do that with sinfo, and in this case, I'm passing in a formatting option to give these particular fields or columns back for each of the partitions. So I list the partition, whether it's available, the number of CPUs, nodes, and memory in that partition, and then a compact form of its state, which will show whether it's available or being fully utilized, or perhaps it's in a state we call draining, which is where all of the jobs are being completed, and once that's done, it's just rebooted. And then you may want to list your accounting groups, which you can get with this syntax: S account manager, show user, who am I, option S format account, and this %30 just means show 30 characters. So this lists all your SLURM accounting groups. So for instance, one that I'm in is this pipelines group that I've listed. And so this is essentially to help us with our reporting and our fair share of resources, so that when you submit a job under a particular project, we appreciate if you can use this syntax to specify the account, so that our reporting picks up that you've used so many CPU hours or so many resources for that account, and we can ensure fair share of the cluster. And so in this case, for srun, salloc, or sbatch, in the case of sbatch, you have to put these parameters after the sbatch keyword in the file. So in this case, I could submit to the HighMem partition under a specific account. So I do srun partition equals HighMem, this account and this job name. Or in the case of using GPUs, I could submit to the GPU partition in this way. And then there are a number of advanced commands that you could run during your job's running or even afterward. And some of these use the job ID as input. Now the job ID is given to you, printed to your screen when you submit an sbatch file, or if you're running srun or salloc or something like that, you can get it from SQ by querying the queue, maybe passing in your username, option U, and then your username, and this will show you the job IDs and various statistics about that. This is only for running jobs, or if you want it for completed jobs, you could run saccount. So say that we had a job running with this particular job ID, I could run scontrol show job ID and then this ID, and this gives you quite extensive information about that job that's running, including your working directory. And there are ways, if you need to even change some of the specifications of that job while it's running. So this is a useful way to interact with that. We could then, for a job that's being run or that has run, use saccount with this advanced syntax. So in the first case, I'm querying the job and asking for these particular fields or columns to be shown. And so in this case, I want to see the job ID, and this %-15 just means show 15 characters of that, the job name, the partition account, how much time has elapsed with that job, if any, the number of nodes, tasks, and CPUs that I'm using, and this I'll explain toward the end. It's essentially ways to run jobs over multiple CPUs or tasks or even nodes. And so if you're running such a job, you can see the number of nodes, tasks, and CPUs that you're using. And then for jobs that have completed, you can output the maximum disk read and write, list of nodes, and then max RSS. This is a value that corresponds to the maximum amount of memory that's being used in that job. And then the CPU time, which for multiple CPUs is longer than the elapsed time. Since you're using many CPUs, it will accumulate the total time as though it were run on a single CPU. And then the state, which is whether it's running, completed, failed, cancelled, so on. And then the exit code, which is 0 when it's successfully completed, or non-zero if it's not successfully completed. And so that's kind of the long form to do with running and completed jobs and various bits of information on that. We can also query particular time ranges. And so in this case, I use option S for the start time, option E for the end time, and then this option X just means compact form, where it's a single row per job, rather than if you have many steps within that job, it doesn't display those as additional rows. And then again, I've output various information, including the start and end time. So this is a way to query specific time ranges where you may know of a job that was run in a certain time range and you want to know the status of that job. And then continuing with the advanced commands, we have these email parameters. You can see this in the SLURM documentation, or we have this simplified version on our own documentation. So this is a way where you can be notified via email of the status of jobs. So for instance, you have this mail user field and you put in your email address there, and then this mail type, and you put in your event types, which is a comma separated list. I've included some that you may want to include, but there's more that you can see listed in the documentation. So we may want to know when the job begins or ends or fails, or even reaches its time limit and is cancelled. And so this is a way to be notified without having to continually log in and check on the status, but just getting an email about it. And then there's also a way to exclude nodes with the syntax exclude equals and then the names of the nodes. So you can use the syntax SLWRK dash and then the number. In this case, you can do comma separated or even ranges. And this is where you have problematic nodes. For instance, if you know that there's a problem with the node, perhaps the file system isn't mounting or something like that. Obviously, we appreciate if you let us know that that's the case. But if for some reason we can't immediately attend to that and you need to run your job now, you can exclude that particular node by using this syntax. Another advanced use case for SLURM is array jobs. And this is where you can quickly submit many similar jobs, each with the same resources, and without the need to manually launch all of them. And so you could, for instance, launch many tens or even hundreds of jobs instantly to the queue, and then depending on your particular configuration, many of those can be run at once. Ideally, you'll pass in the array task ID. So this is the thing that iterates as you move through your job array. And you would want to pass this into whatever script you're executing, which would ideally change the behavior of the job that's run each time. And so you may, for instance, pass it in to provide a different selection of input so that that particular job within your job array does something different to the previous one and the following one. And you can also use it for a kind of special use case of running a serial process one after the other. But that's also achievable with dependencies, something that I'll present a few slides later. So for example, I have this syntax in an SBatch file. What I'm doing is running 20 jobs with 5 of them being run concurrently or simultaneously. So I use this syntax, array equals 1-20% 5. You can use 0 to 19 if you wish, but in this case, I've chosen 1 to 20. And so later down here, my SLURM array task ID starts at 1 and it goes up to 20 as I move through my job array. And then this 5 is showing that I'm running 5 at once. And so once one of them completes, the next one will be launched and so on. Presumably all 5 end at about the same time, and then another batch of 5 are run at once. And then I'm using this special substitution here that I'll show in the next slide in order to differently name my output logs so that I can see how each of the different job arrays, jobs in the job array are being run. And then I'm emailing myself, and in this case, I use fail and array tasks. So this notifies me for each task in the array if it fails. So rather than just the whole job, the whole set of 20, and whether that fails, it will actually notify me individually for each one. And then you can see I'm passing the task array ID in as input. So this means that it's changing the behavior that's being performed for each job in the job array. So moving on to the substitutions and environment variables, this is what I referred to before. You can see the different options at this URL here. So this is essentially where you want to, for naming output logs, either the standard out or the standard error, you can substitute in something that you don't know the number or name of until you launch your job. There's also an equivalent environment variable which you can use to name outputs of specific software or otherwise refer to in some way. So for instance, we have the job ID of the running job. You could substitute %j into your file name and it would place the job ID there instead of %j. You can also refer to this as SLURM job ID, although all of the environment variable cases you don't put in the file name, you rather refer to in some other part of your SBatch file. And I'll show an example of this later. You've also got the job name, which is %x or SLURM job name. You've got, for job arrays, the master job allocation number. So this is only one for each job array job. And this is %A or SLURM array job ID. And then the job array task ID, this is the index that's changing. This is %a or SLURM array task ID. And then you've got the CPUs per task, SLURM CPUs per task. There's no equivalent substitution, but the later case is useful for when you're doing multi-CPU jobs and it may be necessary to export this as OMP num threads equals. And this is telling OpenMP, which is a software that manages running a process over multiple CPUs. This is saying this is how many you can use. So to show an example of this kind of substitution, so I'm just going to jump ahead a slide. This is the kind of thing that we can do. So this is just a single job and my output is log/%x-%j. So this is going to name the log file the job name dash the job number dot out. And so this is the kind of way I can do that. Now, I talked about interactive jobs last time, but just to expand a little. So if you're running an interactive job, we expect that you're running a short process that doesn't utilize a lot of resources, although you could do this for some quick interactive job. But generally, we expect that the runtime will be short. Otherwise, you should probably just be running an SBatch file. But actually, if you do specify a shorter runtime and less memory, if you can afford it, this increases your chance of your job launching immediately rather than having to wait in a queue. And so if we do this in several steps, we could either use salloc or srun pty bash. I've used srun in this case. So I can call the program, I can launch bash in this way using time equals 1. This means 1 minute. And then memory equals 1 GB. And so this puts me on the compute node where I can then run Singularity and shell into this particular container. And in this case, I'm calling this particular radio astronomy software CASA. And so this is doing it in steps, first connecting to the compute node, shelling into the container, and then running the software. And this is all from that point on interactive. Or you could do this in a single call using this syntax. So I do Singularity exec, the container path, and then the software. But the problem is you could run a script after this, but I don't know why you would versus just running an SBatch job. But otherwise, if you're not running a script, you could must be manually processing after that. And all of your output is just printed to the screen. And so, as I'm saying here, if you do it in this way, your jobs run within your bash session, all the outputs printed to screen, and the whole process is volatile. This is the case when using srun or salloc or even screen or tmux sessions, if you know how to do those. These are all okay, but they're subject to restarting the SLURM node, the SLURM login node, which has to be done time to time, unfortunately, meaning that all of those sessions would be lost. But if you've run an SBatch job, that's completely done on the compute node. So restarting the SLURM login node would have no effect on that. And so that's one advantage. The other advantage is that it's backgrounded and that it writes to your log files, so you can just come back to it later. And if the queue is full, then you don't need to worry about waiting for it to launch. You could just submit it to the queue and come back to it later. So here's an example of the previous job, but where I've put it all within an SBatch file. And in this case, I'm passing in my script, and I'm also naming the CASA output log according to these environment variables I mentioned before. And then lastly, for advanced SLURM commands, we can also use dependencies. And this is where you allow a job to be scheduled for running based on the status of a previous job. So for instance, you may only want to begin this job once a previous one has completed successfully. And the syntax for this, if we're running SBatch files, is Option D, and then you could, for instance, use after OK, colon, and then the job ID. And so this is saying after this successfully completes, then you can run this other job called another job. And then this kill on invalid dep equals yes means that if this job ID fails, on which we're dependent, then cancel another job.sh and don't leave it in the queue because the previous job failed, so we don't want to continue with that job. And then we could also use this after any syntax, and this is where you are saying after any completion status, whether it's successfully completed, whether it's failed, you want to run this next job anyway. And you can pass in multiple job IDs as comma separated, as you can see there. And so that brings me to parallelism. And this is the kind of thing that you would be doing if you're using multiple CPUs or multiple nodes or tasks on our clusters. So the Oxford definition for parallel processing is a mode of operation in which a process is split into parts which are executed simultaneously on different processes attached to the same computer, or I would add, or different computers attached to the same cluster. And so just to clarify the scenario and the language, a cluster includes many connected nodes, each with its own memory and number of CPUs. And in this case, the nodes are single computers, or you could think of them as servers or VMs or machines or even boxes. And so we're talking about many connected computers within a cluster. Some processors can make use of many of those at once. Some can make use of many CPUs on one node. And so this is the kind of thing we're talking about and how to do that. So in order to process in parallel, you often partition the work into smaller jobs, each receiving a partition of the data set and performing its work and then bringing it back to the master worker, which is able to accumulate all of the work completed amongst all the workers and then go from there. And sorry, just to mention, I guess this is pretty much standard for a lot of big data sets in current day research, particularly if we think of the Meerkat telescope. You have to transfer the data, process the data, visualize the data, all using this kind of high performance computing infrastructure. And so you can achieve parallelism on a single node using OpenMP. And this distributes the work over many CPUs. And typically, yeah, as I say, this uses OpenMP. There are other programs that can do it, but generally it will be OpenMP. Or you can distribute the work over multiple nodes. And so this would be multiple tasks per node, or even if you have one task per node but many nodes, it's still many tasks in total. So that's the language to use there. And each is given an amount of memory and an amount of resources to use. Generally, we're talking about a cluster when we're talking about multiple nodes. And typically we're talking about OpenMPI or MPI, message passing interface. And so in order to do this, you require an MPI wrapper. There's MPI run, AP run, S run, which is SLURM's version. Or if you're using the CASA software, you use MPI CASA. And SLURM is what manages this on the ilifu cluster. So to give some examples, so normally we would be, for many jobs, many processes, we're actually only using one task, one CPU and one node. And so you could refer to this as one thread, where I guess a thread is either, it comes down to a CPU, and you're either talking about one of many CPUs in OpenMP or one of many tasks with MPI. So this is the default for a lot of processes, and when you just run srun or sbatch and don't specify these arguments, then it's always one. Now you could run an OpenMP job in SLURM, and then you would be using the CPUs per task argument, and that would be more than one, while the nodes and tasks must stay at one, unless you're also using MPI. And as I showed before, you might also need to export OMP num threads. And then if you want to implement an MPI job, you would use more than one task, but the nodes and CPUs could still be one. And you would be using the nodes n tasks per node parameter, and perhaps even that CPUs per task parameter if it can do both multiple CPUs and multiple tasks. And as I said before, you need to wrap this in an MPI call. And since you'll be using Singularity, the order is to wrap Singularity in MPI. So the MPI wrapper first, then the Singularity call, then the software. And whenever you're doing this, you can never exceed 32 CPUs or 32 tasks per node. And so the product of n tasks per node and CPUs per task can't exceed 32. And in fact, SLURM won't let you request such a job anyway. And so here are some examples. So if we're using many CPUs on one node, we would say nodes equals 1, n tasks per node is 1, but CPUs per task, for instance, is 8. I can also specify the memory as per CPU rather than per node. And so this is how I would run an OpenMP type process, and then I would Singularity exec Python my script, assuming your script has implemented this or calls software that can use OpenMP. And then I could use many tasks within one node. So I could set nodes to 1, but then n tasks per node to 16 and CPUs per task to 1. And then I would need to wrap it in some MPI call, and then again run Singularity and my script, where the script would need to have MPI implemented. And then we could use an sbatch job using many tasks over multiple nodes. So in this case, I would set nodes to more than one, in this case 2. And I could use 8 tasks per node and 1 CPU per task. And then I could do memory 10, and this means memory per node. So in total, there will be 20 gigabytes allocated. And this is if your software can utilize shared memory across nodes. And so again, you would need your MPI wrapper, and then you call Singularity and your script. Or you could even use both. You could use many tasks and many CPUs. And in this case, within one node, you could do it over multiple nodes. In this case, I'm doing one node, 4 tasks per node, and 8 CPUs per task. So this is using all of the CPUs on that node. And in this example, I'm calling the MPI CASA wrapper, and then Singularity, and then this particular container where it's been built to enable MPI, and then I'm calling some tclean script. This is a specific CASA task where you can utilize both multiple CPUs and multiple tasks. And so this is a good use case for that kind of job. And so that brings me to demonstrating how to write and run pipelines. So what I'm going to do is demonstrate the IDIA Meerkat pipeline. So this isn't to demonstrate something about radio astronomy, but rather how you could build a pipeline for any kind of research field. And it shows you kind of at the SLURM infrastructural level what you would do. So I guess it's a good framework in that it's a parallelized package for HPC processing. It uses a particular format called a multi-measurement set. This is the file format, and this is what enables you to parallelize across the cluster. And it outputs your final data products essentially with the push of a button. And what it does is dynamically uses resources for different steps within the whole pipeline, and it submits that to the queue. And each step is its own script or job that does or doesn't use MPI, and optionally can use a different container. And then you can even insert your own scripts into any step within the pipeline. So let me now demonstrate that. So here's something I was working on earlier. So this is the particular software process Meerkat, and I'm calling, I'm passing in this particular raw data set. I'm running what we call the build step. I'm using a particular reservation that was set up to make sure that I can actually run this right now. So this has gone through and it's built this configuration file. And so you can see here, it has a whole bunch of specific astronomy stuff, but what I want to point out is this SLURM section. So this has read the data set and it's decided the kind of resources that it might want to request. I'm actually going to edit these since I'm not going to be using that many nodes right now. And then I'm also just going to quickly change this to 1 so that it's a bit more straightforward. So what I can then do is I can run this, sorry, let me actually just go into a bit more detail there. So this shows you the kinds of resources that are being used for steps where it is able to utilize MPI. And it has a path to a container, which you can change, has a path to your MPI wrapper, which you can change. You can even pass in dependencies, that is SLURM job dependencies. So it's only run once those are completed. You can change your account and you can change your reservation. This is if you need a reservation of particular resources allocated to you, but this won't be the case for most people. And then a lot of the action is in this field, scripts. And so I'm calling various scripts, and then I give the name, which will find it in a particular path. I then set this to true or false, and false means this cannot use MPI, and true means that it can. And so these are separated into steps so that you're not trying to request many resources for a job that can't actually use them. And then I have this empty string, which means use the container specified here, but you could pass in a different container and that uses that container for that step. And so this is a good way, pardon me, this is a good way to, for different steps, use different resources and potentially different containers. And so I can go ahead and run that, and then that goes and it writes this submit pipeline thing. And then all this does is it submits the S batch files in order. It grabs the job name, and then it stores that as IDs. And then for IDs, each step is run as a dependency depending on the previous IDs, and it will kill it if the previous dependencies fail. And so it just goes through. It's quite simple. It just submits them one by one and accumulates the job IDs as it goes along. And then it writes a number of these kind of bash ancillary scripts that interact with that. So I could go ahead and submit that pipeline, and it gives me the job IDs, and then it gives me these things that I can interact with. So I, for instance, could show a summary. I might just minimize that. And this is able to show me the job ID, names, partition, and all the stuff I showed before. You can see one of them's running, and you can see the resources that I've requested for each of them. And then after this is run, it's got these ways to display the run times based on the logging output, which has the timestamp. And then it can find errors, looking for particular error codes. And then which I will do, it can also kill the jobs, and that's just essentially cancel and then all the job IDs. So I think this is a good way to write your pipeline, where you can use different resources for different steps and potentially different containers. Just to show a few more things quickly, one of the first steps is where we do this partition. This is an example of a job that utilizes multiple nodes and multiple tasks. So I've set those there, and then I explicitly export OMP num threads. And then like before, I pass in the MPI wrapper. I have the singularity call, the container path, the software option passed into the software, and then I'm calling my own script, and then I have input into that script. So that's the order of doing these things. You wrap singularity in the MPI wrapper, and then you wrap your software in the singularity call, and then in this case I can also pass in a script into my software. And so that's just a generic demonstration of the kind of thing that you can do within writing when you're trying to write pipelines. And you're welcome to look at the documentation there to see some more detail about that, whether you're interested in the algorithmic details or the kind of SLURM infrastructure details. Just to cover some miscellaneous things, I wanted to mention symbolic links or symlinks. These are shortcuts to other file paths, and this is useful when you want a shortcut to your own directory. So such as linking, my Scratch directory to my home directory called my Scratch. And it's particularly useful for Jupyter. So Jupyter only mounts your home directory. It doesn't mount Scratch and whatever else. So if you want to access files in Scratch, then you have to symlink first, and then you could navigate to your Scratch directory through that symlink. And in fact, we set up a number of symlinks for you, including for Soreo data in your IDIA projects directory. So for instance, the Mighty project has this symlink, which just points to the raw data actually at the /Soreo file path. There's also the miscellaneous use case of aliases, which are essentially a good way to store long commands as a shorthand command. And so in this case, I've got SQ set up as SQ option U, who am I? So this shows my jobs in the queue. And then for this one that I've showed before, where I call CASA with particular resources, I could set it up as a CASA SLURM alias, and this is tab completable once I set it up. In this case, I've got mem and CASA as environment variables that I have to set. So this is just whatever memory I want, and this is whatever path to the container. So you can put these in your bash profile, which is loaded upon your login. I could just quickly show my one, for instance. So you can see I've got this SQ alias, and so whenever I want, I can just run SQ in this way, and then I've got this CASA SLURM thing, but where I've specified this is the container I want to use, this is the amount of memory I want to use. There's a bunch of other things you can do, like you know, this particular S account output that I showed before. I have this set up as summary, so I can just say summary, and it shows me, okay, all of these jobs before were cancelled or completed that you were trying to run. So that's another helpful alias to use. Now, I wanted to very quickly demonstrate Globus and just remind you, we talked about this last time, but essentially there are a number of different services for data transfers. You are not to use the SLURM login node for this, so you should not be running SCP or rsync or move or copy on the login node, since this can lead to poor performance for other users. You also shouldn't be writing large files to /users, but only scripts or config files. For temporary data, you put it in Scratch. For long-term data, you put it in your particular user account for your main accounting group. So it might be IDIA users or ilifu bio users or Astro users and so on, or even CBio users. This is where you store long-term data. We have this transfer node set up for rsync and SCP, or even internal CP from one location on ilifu to another. And so this is the kind of syntax you can use there. But for faster transfers or even more frequent transfers that are smaller or even heavy transfers, you should be using Globus. Now, I'm not going to go through all the details. I presented this last time, but just to quickly show you. So you can install Globus as on your laptop, which comes up here. Now, just to quickly show you on the documentation, we have quite a number of links to various other bits of documentation. So I'm not sure why that's not loading. There we go. So it shows you how to set up Globus online, how to log in with, for instance, your university's credentials, and then it shows you, kind of steps you through in a quite simple way how to set it up on your own laptop. Here we go. So for instance, it's got Linux, Mac OS X and Windows apps. Here's the example for Mac OS X from their website. It's very simple to set up and you can just go through that. Now, once you've done that, you'll be able to have this kind of thing. So this is where I've connected to the ilifu DTN. So for instance, I've got this shortcut to my Scratch directory, which has Globus demo. And then from here, I can say transfer or sync that to my laptop. Okay, I've lost the shortcut here. I'm running out of time anyway, so I don't think I'm going to show this extensively, but you can, for instance, look at the different contents on your own laptop. So this is an empty folder I have on my laptop. This is a particular directory I have on the ilifu DTN. And then I can just say transfer, start transferring from here to here. I could also do the reverse. I can look at the activity and this tells you how it's going. I can also get an email that tells me whether that succeeds or failed or whatever. And so it's quite user friendly, but then it's also using quite a heavy compute backend, which is good. And so that's that. Sorry, I meant to remove this slide since we're presenting that next time. The last thing is CARTA, and this is something set up for astronomers, and this is available as the URL carta.idea.ac.za, and this is where you would log in with your Jupyter credentials. You can browse through the CARTA share directory. So this is something, so you can go down to the astronomy and then CARTA documentation. So only the CARTA share directory is mounted here. So if you want to look at files, you have to move them to there. In fact, ideally you would convert them to HDF5, even if it's only a single channel. There's still many advantages. And so you would use this syntax that would place your HDF5 file here, and then you could browse that. And you can look at all sorts of things like the x-axis, the z-axis, sorry, the y. There's also a z-axis, and there's contours, which you can pull up. And I won't go through in detail how to do this, but you could play with that. There's also world coordinate system matching. So once you load in another image, you can match them and blink between them. There's also all sorts of things like drawing regions and looking at statistics within those regions. Yeah, I think it would be actually good to demonstrate this at a bit more length during the applications training, the next online workshop we're going to run that Jeremy mentioned. And perhaps before then you could have a play with it yourself, and then if there's questions we can demonstrate a bit more of that. But for now, I guess I am going to leave this best practices slide up. I also presented this last time. It's just a reminder of the kind of way you should be utilizing ilifu and the SLURM cluster. So I'm going to stop there and we can take questions. Jeremy and also Dane and Mike, if necessary, can step in and answer questions. Unfortunately, I have to leave in 5 minutes, but if we continue after that, Jeremy can keep taking questions, or of course you can always email ilifu support and we can contact you there. So thanks for listening.
Thanks so much, Jordan, for a fantastic presentation. Yeah, as Jordan mentioned, we'll be able to take questions now. If you would like to either, you'll have to unmute yourself to ask a question. Alternatively, you're welcome to post a question through the chat, which we'll read through and comment on. Otherwise, you're also welcome to email us at support@ilifu.ac.za for any support related questions. But yeah, if anybody has any questions there, welcome to ask now.
I have a question.
Sure, Jacinta, go ahead.
Where should I be storing my FITS images if I'm storing the just the HDF5 files in my CARTA shared directory?
So for CARTA share, the directory structure is divided up into 2 areas. One is a user space, so each user has their own personal folder that you can place HDF5 files in. And then there's also group areas where projects are listed. So if you wanted to share your output with a particular group, you could place them there. Sorry, just to confirm the question, did you mean the FITS images prior to converting to HDF5?
Yeah, that's correct.
So those, well, what's useful is to, because generally you only want to view the HDF5 files with CARTA because of it provides much greater performance. So you can store the FITS images in your user space, such as like IDIA/user/Jacinta. Otherwise, if they're project specific, you can place them in a project directory. But I think Jordan showed there's an srun command in the documentation that basically converts the FITS to HDF5. So it doesn't necessarily matter to have your FITS in the CARTA share directory, because if you run that command, it'll place the HDF5 in the CARTA share automatically.
Yeah, so that's my question. So I've got my HDF5 images in the CARTA share directory, in my user CARTA share directory. But I've also got my FITS images in there. I'm just wondering whether it's better to store them in there or in my IDIA user space.
It's probably better to store them in the IDIA user space. It's easier for us to take into account. I think they're also probably slightly larger, if I'm not mistaken. And like the HDF5 files are perhaps temporary, whereas you want to keep the fits for longer, right? So I would suggest storing them in your the IDIA users folder.
Okay.
Yeah, just to add to that, so because only the CARTA shared directory mounts for CARTA and you can't access the other file systems, you have to duplicate the data anyway. I mean, you could just move it to CARTA share, but I agree with Jeremy, it's best to store elsewhere, particularly for long-term storage in your, for instance, IDIA users directory. And so if you are to do that, then in order to get it into CARTA share, you have to duplicate the data anyway, in which case you may as well just place the HDF5 version in your CARTA share directory. And toward that end, I have this little thing that I write, which just essentially is the same kind of thing I showed before, but it takes whatever fits file I've passed in, and it puts it in my CARTA share directory. Well, it converts to HDF5 and puts the output with the same name, except instead of .fits, it's .hdf5. And in fact, you can also utilize many CPUs per task for this. So that's something that you could use to put the HDF5 file in your CARTA share directory.
Cool, thanks.
We've had a question from Javan, who has asked if the job parallelization reduces the job runtime compared to the standard method of submitting jobs. Javan, it should do. So, for example, like a use case would be if you look at like astronomy data as an example. Astronomy data is often divided into different frequency channels, and the data reduction process can be conducted on each of those frequency channels individually without influencing each other. So it may be possible to run, say, 50 smaller tasks by separate out the data into 50 different partitions. And this should then run at a 50th of the time instead of sequentially running the data processing. So yeah, the parallelization should indeed reduce the job time on the cluster. It should improve sequential running of jobs, but there's obviously often an overhead related to parallelization where certain parts of a job requires sequential processing or serial.
Hi, Jeremy. Can I ask a question?
Sure, Victoria, go ahead.
Hey, Jordan as well. Sorry. Sorry if this is a stupid question, but this is all really new to me. I just wanted to find out, Jordan was speaking about when you have a bash file, a job that you're writing a script, right? And you've got to specify how many nodes you want and how many tasks per node and how many CPUs per task and everything. How are you supposed to know how many to specify? Like, how do you know what you need for your job?
Okay, so to start off with, it depends on the software. So if the software supports threading, which is often uses OpenMP, that allows you to have multiple threads, and so you can have additional or more than one task, but you have to you only use one node, and then the CPU usage often depends on how parallelizable your data is. So if your data can only be split into 2 parts, then it's probably not worth having more than 2 tasks or 2 threads. However, I presume with bioinformatics data that with gene sequencing, there's probably a lot of, you can probably divide your data up a lot more and parallelize it a lot more. A lot of it is trial and error, like testing the resource usage. Yeah. I don't know if Dane wants to weigh in on this.
Not particularly. I agree with what you say. Mostly it involves going to the documentation of the particular software you're using. So if you were using bed tools, for instance, I think there's probably an option -- threads or something. So that's the parallelization on a single node. I don't think it expands across multiple nodes.
Okay. So I know in some of the like singularity commands that I need to write, like there's I write T and then number of threads, like in that command. So that's different to the above section where you write S batch and then all of your stuff.
So
yeah.
Go ahead, Dan.
No, you go ahead.
I would, so if you say you had 32 threads, or you can actually have more threads than the number of CPUs, I guess, on a node, because even if you maxed out that, it would only run say 32 threads, and then it would start on further threads. But if you need to say like 16 threads, then there's no point of having more than 16 CPUs on a particular node.
Right. Okay.
So there are two parts to it. The one is you need to find out what the software wants or can use, and then there's on the cluster itself what the resources that you're requesting.
Okay.
If that makes sense.
Yeah, that's cool. Okay, cool. Thanks, guys. Thank you.
Sure, Victoria. If there are any additional topics that you would like us to cover in these training videos, you're welcome to let us know here or email us at the support ticketing and just provide feedback or suggest topics. I'm just going to check through the chat. All right. If there are no other questions, I think we'll close off here. We'll have the second advanced training session, probably in 2 to 3 weeks, depending on how or when lockdown ends. But we'll email all users about that information. Thank you, everyone, and thanks for the feedback. Okay.
Awesome. Thank you, Jeremy. And everyone.
Thanks, Chris.
Thanks, Jeremy. Thanks, Dan.
Cool. Cheers, Victoria. Thanks for coming.
Thanks, Jeremy. Cheers.